Welcome back to The Explainer. If you're a focused learner looking to seriously upgrade that mathematical toolkit of yours, well, you're in the exact right place today. We're going to be stepping into the shoes of a calculus detective. Our mission, cracking some of the absolute most complex convergence mysteries out there. We're taking the theories right from our source lectures and transforming them into your ultimate investigative guide. So let's just jump right in. Up until now, you've probably relied on tests built specifically for series with purely positive terms. But what happens when we throw a little twist in there? What happens when a series isn't just positive and instead the terms flip-flop signs? Plus, minus, plus, minus. Well, this fundamentally breaks the rules we've been relying on. It's a real mathematical curveball, and it means we need a totally new set of tools to figure out if our series is going to settle down to a nice finite number or just completely spiral out of control. To do that, here's our investigative map for today. First, we'll look at the alternating series twist. Then, the two tiers of convergence. Third, the alternating series test itself. Fourth, the ratio and root tests. And finally, number 5, estimating the error margin. All right, starting with part 1, the alternating series twist. So first things first, we've got to identify our main suspect. And an alternating series is, well, it's exactly what it sounds like. A series where the terms alternate between positive and negative. Think, 1 minus a half, plus a third, minus a fourth, and so on. Now, because these positive and negative terms are constantly fighting each other, adding a little bit, then subtracting a little bit, the series might actually settle down to a finite value way easier than if we were just piling on positive numbers. But to actually prove that, we really need to understand the different levels of convergence. Which brings us to section 2, two tiers of convergence. Okay, let's dive into this. Because this right here is where the detective work gets incredibly fascinating. See, in the world of alternating series, there isn't just one type of convergence. There are actually two totally distinct tiers. I want you to think of this first tier as the gold standard, or the VIP tier. It's called absolute convergence. To test for it, we take our alternating series and we literally just strip away all the negative signs. We take the absolute value of every single term. If that new, purely positive series still converges, boom, the original alternating series is declared absolutely convergent. It's basically saying, hey, this series is so inherently strong and stable, it doesn't even need those negative terms canceling things out to reach a finite sum. And honestly, this perfectly illustrates why we love that gold standard. Our source material points out an absolutely critical theorem here. Absolute convergence implies convergence. Bottom line, if you prove a series is absolutely convergent, your work is done. You don't even need to bother testing it for basic convergence because it automatically passes. It is a massive, massive shortcut for any calculus detective out there. But okay, what if it fails that VIP test? What if we strip away the negative signs and suddenly the series just diverges, spiraling off to infinity? Well, don't throw it out just yet. We check for our backup, the second tier, conditional convergence. This means the original alternating series does converge, but honestly only because those negative signs were there to save the day. Remove them and it all falls apart. A classic example from our sources is the alternating harmonic series. With the alternating signs in place, it converges, but take the absolute value and it turns into the standard harmonic series, which, as we know, definitely diverges. So we'd say it's only conditionally convergent. All right, moving on to section 3, the alternating series test. So, if a series happens to fail that absolute convergence test, how do we actually test the original alternating version? Well, let me hand you your very first specific tool for checking that backup conditional tier, the alternating series test. It's basically a super strict two-step checklist. To guarantee convergence, you just look at the positive portion of the terms. We usually call them B sub n. Step 1. The terms must be monotonically decreasing. That's just a fancy way of saying every single term has to be smaller than or equal to the one right before it. Step 2. The limit of those terms as they head out to infinity has to equal exactly 0. If those magnitudes steadily shrink to 0 without ever ticking back up, this test guarantees the series converges. It really is that simple. Just remember though, this test only proves conditional convergence. It tells you the series settles down, sure, but it doesn't give you that VIP absolute status. Now for section 4, ratio and root tests. Oh yeah, now it's time to bring out the heavy machinery. We're cracking open the power tools used specifically to check for that gold standard of absolute convergence. You can basically treat this scoring system as your ultimate cheat sheet. Both the ratio test and the root test brilliantly share the exact same really simple scoring system. It's all based on finding a limit, which we're going to call L. Here's how you score it. If L is strictly less than 1, you win. The series is absolutely convergent. If L is greater than 1 or if it equals infinity, the series diverges. But watch out for the dreaded third outcome. If L equals exactly 1, the test is entirely inconclusive. It literally gives you zero information, and as our sources point out, you just have to pack that tool away and try a totally different strategy. Now, since both of these tests use that exact same scoring system, how do you know which power tool to actually pull out of the box? Well, efficiency is everything in calculus. So here are the pro tips straight from the lecture notes. You're going to want to reach for the ratio test, which, remember, involves dividing the next term by the current term whenever your series has factorials or exponential terms. Why? Simply because factorials just beautifully cancel each other out when you divide them. On the flip side, you want to reach for the root test, where you're taking the nth root of the absolute value of the terms, whenever your series is dominated by nth powers. Taking an nth root of an nth power just instantly simplifies all that terrifying math into something super manageable.
And that brings us to section 5, estimating the error margin.
Let's pivot to a bit of a real-world application here. I mean, it's great to know that a series converges, but in practice, we usually can't sit around adding up infinite terms. We have to stop somewhere. So how do we use these convergence tools to precisely approximate the actual sum? Well, the answer relies on what is probably one of the most elegant concepts in our entire toolbox. For a convergent alternating series, one that satisfies that alternating series test we talked about, the error of your approximation is never, ever bigger than the first omitted term. Seriously, think about how powerful that is. If you add up the first 100 terms to get an estimate, you know for an absolute fact that your estimation is off by no more than the size of the 101st term. The very next term you chop off literally tells you exactly how accurate your whole estimation is. So let's actually step through the logic of calculating an exact error margin. Let's say, for example, you need your answer to be accurate to 4 decimal places. Step 1, set your error tolerance. For 4 decimal places, your tolerance is 0.00005. Step 2, use that golden rule we just talked about. You just find the number of terms n where the very next term is strictly smaller than that 0.00005 tolerance. Step 3, now that you know exactly how many terms you need, just compute the partial sum by adding them all up. And finally, step 4, state your final approximation. And you can do it completely confident in the fact that your answer is perfectly within the required bounds. You've literally mathematically guaranteed your own accuracy. We have definitely covered a lot of ground today, from the VIP status of absolute convergence to the super clever shortcut of the alternating series test, all the way to the heavy machinery of the ratio and root tools. So, I want to leave you with this final thought. The next time you're faced with a totally new, highly complex alternating series that's flip-flopping endlessly into infinity, which tool are you going to reach for first? Are you going to test for the gold standard right out of the gate? Or maybe immediately check for those shrinking terms? The mystery is yours to solve. Thanks for joining me on The Explainer today, and hey, keep that calculus toolbox sharp.